Hello to everyone. We are here for our next speech by Petar Zecevic from SC Group. Petar is actually a CTO at SC Group and a PhD student at FAIR at University of Zagreb. He has over 17 years of experience with data and AI. And in his talk, Petar will focus on the application of data science in astronomy, giving two concrete examples from his PhD thesis on how machine learning and AI may be used in this field. So, Petar, you can start, and everybody that's joined can ask questions in Zoom chat or see the lecture on Facebook.
Okay. Thank you, Maria. Well, let's start. I don't have much time. So as Maria said, I'm CTO at SV Group in Zagreb, which is a smallish company of almost 50 people. We provide various programming consulting services. I'm also a PhD computer science student at University of Zagreb at FAIR. I'm not an astronomer. And I'm also visiting fellow at Direct Institute at University of Washington because I've been collaborating with them for my PhD. So I've been in contact with astronomers. I also wrote the Spark in Action book. And if you need perhaps a Spark course for your team, I have this shameless plug right now. So you could just ping me, and I've given it, internationally several times, many times in Croatia and banks and so on. So I'll be happy to help if you need it. And my company, SV Group, is JetBrains Platinum reseller. And we prepared 5 PyCharm licenses for you. If you'd like, you can send me an email to this address, and we'll randomly pick 5 lucky winners, and you'll get a voucher for the PyCharm license. And you will also be subscribed to our JetBrains newsletter, but it's easy to unsubscribe, so don't worry if you're not interested, it's not a problem. So what am I going to talk about? Well, since I'm working as part of my PhD on astronomical problems, I had some exposure to astronomical problems, and I've seen that it's really great place if you want to go into data science and apply data science. Astronomy is a really great place to do it. So I've picked up some really interesting stuff along the way. I've attended some talks by some really smart people, and those are the things I want to share with you. And I'll also share things I've been working on as part of my PhD, which are not that exciting as the other things I'll talk about. I'm not, I don't want to pretend to be able to cover this huge topic of data science in astronomy. I'll just give you some examples and possibly some teasers to make you, maybe want to jump in. So what is data science? Maybe someone already gave this definition today. I found it on Wikipedia, actually. So it's a concept to unify statistics, data analysis, machine learning, domain knowledge, and their related methods in order to understand and analyze actual phenomena with data. And what's probably missing in this definition is, which didn't really exist back in '98, is big data, right? Because in astronomy, we really have lots and lots of data that needs to be analyzed, made sense of, and so on. And this is not, yeah, okay, so statistics and big data, I'd say those are the main things that characterize data science usage in astronomy. And it's not specific to data science. You have biology, for example, genome sequences, and physics, for example, what they do at CERN, meteorology, building weather models, predicting weather, and so on. And but modern astronomers cannot really do any data science, any science without data science, because mostly they're analyzing data that's been collected by various telescopes and exists in digital form. So that's the main thing they do. And astronomy is intrinsically, I'd say, statistical. I made up that that term myself, but I think it's true. And there's a large amount of data. As I said, there's big data today in astronomy, so you need some clever analytical tools, machine learning and so on, to analyze all this. So how is it intrinsically statistical? Well, measurements in astronomy are very uncertain to a large degree because light in optical astronomy passes huge distances and goes through various mediums, atmosphere, principal one of them, space dust and so on. And once it reaches Earth, the telescope, you have various imperfect equipment for capturing that light and that information. You have CCDs, electronical photosensitive elements, and you have optics and so on. All of that adds uncertainties and distortions to the light and to signals. And at the very beginning, what you have the point spread function or PSF, which determines the shape a point source produces in the focal plane of the telescope. A point source, that's a term. Well, the stars are so distant, far away from us that they should actually appear as tiny little points. But when they reach the telescope, that light from that point actually spreads around in different ways. And the Airy function is the best possible PSF you can get. And for example, shown here in the rightmost square, that's what you would get in a perfect, excuse me, in a perfect conditions at the center of the focal plane of the telescope. You will get Airy function like this with circles around the main dot in the center. And if you go further away to the edges of the focal plane, you get different kinds of effects and distortions. And not only that, so that's, that depends on the position of the source in relation to the center of the focal plane, but also you have, it depends on time. So the atmosphere fluctuates all the time, as you can see here. And in longer expositions, the images get blurred, so that PSF gets even more complicated. And also it depends on the color of the source, which would mean the color of the filter that was used. So the first step is to model the PSF, and so that's the very basic thing you have to do, and which is critical for other measurements that need to be done on those images. And the modeling of the PSF itself is not trivial. Various methods are used for this. For example, mixture of Gaussians is one possible model that can be used to model PSF. It can be modeled on the pixel level and so on. And usually when an image of the sky is taken, you have usually some known stars at some locations, and you know exactly where they're supposed to be, how bright they're supposed to be. And you can use that information to model PSF at those points of the image. But for the other parts of the image, you have to interpolate those PSF to be somewhere in between those determined on those exact points. So it's not a trivial thing, it's really complicated and critical. And the data processing pipelines that are used in big astronomical projects are really complicated things, and they do this iteratively. First, you need to estimate the level of the background. Then you have to, PSF depends on that, and then you have to determine exact points of those stars. And then once you have first model of the PSF, then you again estimate the background and so on, refine the next PSF estimation and so on. So it's really, complicated stuff. And moving on to machine learning in astronomy, There's also lots and lots of examples here, but just to give you one or two. One ubiquitous example is various sources of light in the image need to be classified. You want to know whether it's a star, asteroid, galaxy, space junk, cosmic ray. And there are different approaches, again, how this can be done, and of course, manually, but if you have billions of stars, that's not feasible, of course. So often some machine learning approach is used where you would get some kind of features from those sources of light, for example, width, height, and so on, and others, and then use those features as an input to your machine learning model, and then train the model on that. Or you can use Bayesian statistics to have a model for stars, model for galaxies, model for asteroids, and then estimate parameters of those models on all of those models on the same object. And then the best fitting model would hopefully represent the true classification of and measurements at the same time of the object. And there was this competition at Kaggle, Galaxy Zoo, based on the open project where volunteers tried to classify galaxies into answer 37 questions about galaxies. How long are the spirals, how big is the bulge and central bulge, and so on. And now that the volunteers have done some work classifying this, the competition was to try to automate this stuff. And the deep learning approach won. It wasn't the manual feature creation, but deep learning where features are created as part of the learning process, right? And one really cool talk I wanted to share with you. I attended a talk by Danny Goldstein at University of Washington, and he's studying the strongly lensed supernovas, which is really fascinating stuff. So supernovas are the brightest events in the universe, as you probably know, and they happen when the star explodes. And when light travels through the universe, it gets bent by, in larger or smaller degree, by gravity, by masses of galaxies, and dark matter, if dark matter exists. We still don't know. But if a galaxy, a supermassive galaxy, happens to be positioned between the Earth and the exploding supernova, effect like this happens. So this is a video from NASA, where the light that goes around the galaxy gets bent and focuses on Earth. So you would get something, some effect similar to this one, where in some period of time, images of supernovas, of the same supernova, appear all around the central galaxy mass. In a perfect alignment of these three objects, you would get a Einstein ring, which is a perfectly shaped ring around the center. But that's really rare, because rarely do we see so perfectly aligned supernovas. So probably you would see something like this. And what's interesting is that this astronomer, Norwegian astronomer Sjur Refsdal, I don't know how to pronounce that, he proposed in 1964 that we can use time delay between appearances of these images of supernovas to measure expansion of the universe, or this Hubble constant, which is the rate of expansion of the universe. It should be, he's shown that this time delay is inversely proportional to the Hubble constant. All these slides are courtesy of Danny Goldstein. I don't know if I mentioned that. Hubble constant controversy is a big controversy, a bit embarrassing in astronomy, because you have two different estimates of the Hubble constant, widely differing estimates. And as the time went by, they became narrow for the error became ever, the confidence of estimate for each of these became narrower and narrower, and now you have the situation like this. So if we could measure, use these stronger length supernovas to estimate Hubble constant, that could probably potentially solve this controversy. And so far we have, there have been only 2 multiply observed detections of stronger length supernovas, probably because we didn't have automatic detection of these is not really easy. But Daniel Goldstein came out with this paper in 2017, and really simple actually idea, but before him nobody proposed it, is that if a supernova appears to be in a galaxy which has certain redshift, and this supernova is too bright, too strong for this redshift, then that's a stronger length supernova, which is a kind of counterintuitive, because the supernova is much further away than the galaxy, so it should be fainter. But it's because of the strong lensing effect, the light gets focused on the Earth and intensified, so it's brighter. So that was fascinating. That's fascinating to me. I hope it is for you. So this would enable automatic detection with this simple criteria, would enable automatic detection, and we can use some big data to try to find the stronger length supernovas. So big data is also a big thing in astronomy, and there's plenty of examples. I'll focus on just 2. That's first Vera Rubin Observatory, formerly known as LSST, and the SKA, or Square Kilometer Array. So LSST, or Vera Rubin, is a huge project. It's currently being built on top of this hill in Chile. It's got the 8.5 meter telescope, not the biggest in the world, but because of its unique design, it goes both deep in the sky and both wide. So it can cover, I think, three times the area, something like that, 3 times the area of the moon. It's got 3.2 gigapixel camera, which is 1.6 meter in diameter, and that's the biggest camera in the world. It starts its operations in 2022, so in 2 years, according to the plan. And it will provide the first video of the visible universe in history, because it will, each night it will cover, every second night it will cover the complete night sky. And it will do that for 10 years. And each object in the sky will get covered on average 700 times. So that's really huge. And each image is 6 gigabytes large. It will measure 40 billion objects. So that translates to 20 terabytes daily, 80 petabytes in total in 10 years compressed data. And it will also provide real-time alerts for when it detects any change in the sky, if supernova explodes or asteroid moves. That will trigger alerts. That will, within 60 seconds of detection, those alerts will be transmitted to the scientific community. So that's a big project. And if you see on the image in the bottom right corner, that shows the optical cables, redundant optical cables put specifically for this project, laid for between South and North America. So that's really big, huge project. The second one I wanted to share is the Square Kilometer Array, and I attended this talk by Michael Wiese from Netherlands, given at ADAS 2018, and he's the head of astronomy at Netherlands. So it's also a really, really big project, international project, and but radio astronomy, and consists of actually two instruments, so-called mid-frequency and low-frequency instruments. Mid-frequency is located in South Africa, consists of 200 dishes in area of 33,000 square meters, and the second one is the 130,000 antennas spread over 0.4 square kilometers in Australia. So unlike optical astronomy, this produces much more data. For example, if you snap a picture with your phone, you get the image that has red, green, blue channels, right? We have 3 channels in the images. And optical astronomy produces images with only 1 channel because they use only 1 filter per image. But in radio astronomy, you get thousands and tens of thousands of simultaneously captured channels, because each frequency is discretized. Discretized frequencies are discretized into tens of thousands of channels, and they are captured simultaneously. So that's mind-boggling amount of data. So here are some numbers. The raw data from the antennas will reach in 2030 100,000 petabytes per day. So there's no possible way to store all that data. It will need to be processed on the fly with DSP, digital signal processing. That will filter out some of it and leave 10,000 petabytes per day by 2030 to be processed in high performance computing. And all of this data needs to be transferred by tens or thousands of kilometers. And that will leave about 600 petabytes per year of fully processed science data products. So that's just huge project and huge amount of data. The whole talk was fascinating. If you can Google this guy and his talks, it was really interesting to me. So what do they do with all this data? They put them in catalogs, astronomical catalogs, which are just big databases. And what typically astronomers do is use ordinary SQL to download subsets of the data and then do some analysis on those subsets, because it's not easy to analyze all of those, the whole catalogs. And they produce nice analysis of pictures like this left picture here. So we came up with astronomical extensions for Spark, or Access, which is built on top of Apache Spark, and enables astronomers to do just this, to do efficient cross-matching of astronomical catalogs, and provides also Python astronomy-specific API extensions that are useful to astronomers. It's based on industry standards, namely Spark, and it's cloud ready. So the idea is you can have those catalogs prepared in the cloud, and you spin up your own instances, do your analysis, and spin them, take them down. So we can cross-match ZTF with almost 3 billion objects with Gaia catalog, the satellite, European satellite, with almost 2 billion objects in 315 seconds if we're starting from scratch. There's no cache. And with partially cached data, that goes down to 40 seconds, which is best that I know of. And you can check the docs on this link. And the second thing I'm working on currently is online multifit. As I said, this is not so interesting as exploding supernovas, but it's still interesting to me. The publication is pending, and I'm writing the paper right now. So what's this used for is for estimating parameters of models of detected objects, namely asteroids mostly. And you use Bayesian, a sequential Bayesian updating, where you update your posterior probability distribution, or your estimate of each parameter's probabilities, by using only one image at a time instead of using all the images at the same time. So that's called sequential Bayesian updating or recursive Bayesian updating. And we can then increase image signal to noise ratio, so decrease amount of noise in the images by just using one image at a time, which reduces the amount of memory required, and we don't have to use image coaddition, which cannot be used for moving sources. So in the nutshell, that's it. I remind you of my Spark course if you want one. And also, I'm repeating this slide. If you want a PyCharm license, just send me an email and you will enter the draw. So I'm looking forward to your questions, if any.
Hi, we will wait for some questions. And
Okay.
while we wait, I would like to ask a thing about AI actually being or seems like being a perfect product for the world of astronomy and new scientists that are working in this area. How do you see this, that AI actually enabled a lot of these new explorations and things you are doing?
Well, you know, AI is an overloaded term. It consists of basically machine learning, deep learning, and things like that. So definitely, as I think I've shown, it has place in astronomy, machine learning, and it's used all the time. I haven't mentioned actually time series analysis, but it's really important in astronomy. But NLP, not so much. You don't need to analyze the language in astronomy or to infer what some person wanted to say. That's not really the thing. But yes, definitely AI is there probably is more place for automating stuff in astronomy analysis and some clever tools, building clever tools.
Great. So in a way, it's similar as data science as a word actually being some advanced statistic and analytics that were done before, but some areas had benefits of some additional either programming solutions or automation systems that weren't here before.
Yeah.
And stars don't communicate. They don't have their own language for the NLP usage.
Yeah, there are some signals. If you've read the news, I have read some news from some signals, recurring signals, but nobody managed to decode those yet.
Okay, great. I'm not seeing any questions. I hope this is working in the chat, but you can, for the end, you can say, do you have a need to attract some of the students at the new university or some of the even younger high school kids into this world? Is there any lack of the PhD students or people wanting to do more things in astronomy?
Well, I'm not sure. I'm just a PhD student, you know. I don't do. I would like people to look into astronomy, and because it's interesting, fascinating, and potentially useful. But I think there are lots of people are going into industry. As soon as someone does some good things in science, they easily get stolen by the likes of Google and Microsoft, Facebook, and so on. So I think, yeah, there's lack of young talent in industry and in science. I think.
Got it.
And
I think
I think it would be useful for young people to start their careers in astronomy. Why not?
Definitely. I think for Croatia, it's even good for the, let's call it mainstream prizes and everything that they awarded the Communicator of the Year award to Korado Korlovic, who's working in the...
Well, okay, he's a communicator.
Yeah, so let's say that some more communication is this area could attract some even technically or science keen youngsters in this area. So let's hope for that.
Yeah.
We do have one question for the end. Can you please explain noise reduction using Bayesian updating in imaging?
Well, the thing is that you can do this estimate by stacking images together with co-addition. And then you have one image that has reduced noise or improved signal to noise. The alternative is to use the multifit approach, where you have a model modeling your object, for example, galaxy, and then you use all of the images to fit the model to all of the images simultaneously, and that would give you similar result with what you would get with doing this simply on the co-added image. And in our approach, we're using online Bayesian approach, learning, where you're using not all the images of the object at the same time, but one image at a time, and then you update the posterior with each new image you get. So in a sense, you are reducing, you don't see it, but you are enabling your estimation process to be efficient, as though the signal to noise is improved, but using only one image at a time. So I hope that answers the question. You're muted, Maria, sorry.
Hi again.
Yes, yes.
Thanks for the answer. For the end, there was one nice comment. An attendee wanted to say, I just want to say how much I love this subject, so that's good to have this in agenda. And they want you to recommend some literature regarding to that question. So maybe put something extra on your pages, or send to Alexander, similar to laser science thing, and etc. So thank you, Petar.
Thank you.
And, thanks everybody. We may proceed to the last lecture and other link to our final talk of the day, Ethics in AI by Mr. Agarwal.
Thank
Bye.
you. Bye-bye.
Thanks.